I give a short overview of current activities in a way forward, what we do with the global system, the integrated forecasting system of ECMWF. This is, of course, always joint work, so I put on the slide here all the names of the member of the ECMWF development team, but we do all this work in close collaboration with the CAMS contract on developments for aerosols and chemistry, for the emissions, for the evaluation, and so on. So the points I want to talk about is the next upcoming cycle upgrade to 48R1. This is meant to be implemented at the beginning of the next year. Another very important aspect for CAMS2 is the preparation for the next reanalysis dataset. So we have to start the production of this dataset in the beginning of 2024. So we have now 1.5 years really to prepare all the model versions and the input data, the satellite data. Also ongoing at the same time are the technical things which have to do with improvement of the performance, computational performance, and also with the move of the supercomputer or our new supercomputer at ECMWF, which is now located in Bologna. So talking about this new cycle, I list here main features which are new. And the most important one is that for the first time we will have stratospheric chemistry using the CB05 Bascoe scheme. We also made improvements in terms of the emission processing. We have sectoral emission input now. We upgraded our anthropogenic emissions, as already discussed this morning, to a version 4.3. There are several updates to the chemistry and the aerosol modeling, and Samuel Remy will talk about this in the talk after my talk. We introduced the Farquhar photosynthesis model, and this will also be mentioned in Philip Palin's talk, I think. So these are model developments. In terms of the satellites that we assimilate, new satellites are AOD retrievals from VIAS, which is very important, and we also added carbon monoxide from S5P to the datasets we are going to assimilate. Starting with this cycle, we already have NO2, O3, and SO2, and there's also a volcanic SO2 tracer. So I want to introduce this fact in a little bit more detail, that we now really have stratospheric chemistry fully resolved with a chemical scheme. Starting with the in 2014, when we moved to the CB05 scheme, we didn't have stratospheric chemistry anymore. We just had parameterization of the ozone chemistry using the Cariol scheme, and later on the HLO scheme. And this scheme served us very well, but of course it had limitations. At the same time, in the background, or not in the background, we developed or we introduced chemical schemes from the Mozart model, from the Mocage model, and from Bascoe, and all these schemes had chemical mechanisms for the stratosphere. And this plot should show the benefit of this. What we see here is the development of ozone at 50 hectopascals over Antarctica in 2020, which was a year where we had a very strong ozone hole, and the observations or the reanalysis is shown in red, so that's our truth. But this was anomalous, and that can be seen from the green curve, which gives you the average conditions, so the climatology. And using now this HLO scheme, this simple parameterization, which is shown here in blue, we see that this scheme, because it's very much linked to the climatology, didn't manage to really produce this very severe ozone hole, because it always wanted to go back to the climatological values. When we used the chemistry schemes, which are shown here in the black curves, they were much more able to reproduce the special conditions in this year. Now we will have the CB05 Bascoe scheme. So what are the benefits for the users of having a scheme for the stratosphere? So first of all, we have tracers which were not introduced or which were not part of our system, which are very important for stratospheric chemistry, the halogenic species. And this can be shown or can be demonstrated also when you look at this plot on the left-hand side, where we see a comparison of observations represented by MLS in black, and then the blue curves are always the curves with the CB05 Bascoe scheme, so the new scheme that we are going to use in 48R1, and the red scheme, the red curve are the curves from our existing system. So in the plots where we don't have any red curves, these are the new species that we get, and I think there will be many interesting science options because of this, and even also possibilities to do data assimilation. For other species, like species of the nitrogen cycle, we get improved stratospheric representation, which can be seen by the fact that the blue curves in those plots agree much better than with our current system. Unfortunately, I don't really know how to go back, the red, yeah. And then at the very bottom, you see a plot where those curves actually agree, and this is ozone. So in terms of the ozone analysis, we don't see so much of a difference by using a full scheme, and this has to do with the fact that your observations fully constrain the ozone in the stratosphere, and that's why the underlying modeling approach does not matter too much. So do we see any improvements then for ozone, which is so important? No, there are improvements, and they come in forecasts. As I pointed out at the beginning, the parametrizations have the tendency to be very close or to move back to the climatological values. And this already shows off in a 4-day forecast. So the summary of this plot is here that if we look at the 4-day forecast, which is shown here in this red curve, the errors are much larger if we use the HLO scheme, the parameterization, the simple scheme, and moving on to the full representation of the chemistry really improves the forecasts. So we also see an improvement for ozone, not directly in the analysis, but in the forecasts. Now moving on to another topic, and this is the introduction of AOD, retrieval assimilation coming from the WIRS product. As you all know, it heavily relies on MODIS, but the MODIS AOD or the MODIS instrument is relatively old and is going to be decommissioned. That's why we really had to find a replacement, and that's the WIRS product. The data are similar, but not the same, and Sebastian Garrigues did really a lot of work to compare the different data sets. I give you just here a snapshot. So on the left-hand side, you see a zonal mean plot from from AOD, from the different two MODIS instruments, and also from two sets of WIRS instruments. So they agree in general, but there are differences for specific areas. And this can be better seen on the plot on the right-hand side, where we show the differences between assimilation runs, where we on one side only assimilate WIRS and on the other only MODIS. So AOD increases over biomass burning regions when we have WIRS, and it decreases over the ocean background and in areas that are dominated by dust. So these are the differences. Are these differences then improvements? And this can be shown in this plot. And the experiments that assimilate WIRS have a smaller biases. And that's, I think, also a good result, that we are now more future-proof. We don't rely on MODIS. We have a replacement, but we also, on top of this, slightly improve our AOD results. Now, one slide also on the emissions. I think we discussed the emissions in a lot of detail this morning. So I just want to say that in the new cycle, we will use version 4.3. And we find that the realism, especially over areas like China, is better than in a previous data set, which can be demonstrated when you look at the upper plot on the right-hand side. So the new emissions, these are the emissions over Asia from 2000 until 2020. And the data set we are going to use is the one in red. Previously, we had used version 4.2, which is shown in blue. So the trends were not properly represented. It's maybe also worth noting that the trends in the version we are going to use, 4.3, are not as good as yet another data set, which really uses a special emission data set, regional emission data set over this area, but they are definitely an improvement with respect to the data set we had used so far. And also for other regions, we can see as a package improvements when we use the new emissions. Oops. Okay, now I wanted to show you one slide where we don't sort of focus on incremental changes from going from one cycle to the next cycle, but just go back and look into CAMS 1, how over the whole period since 2015, the performance of the global system changed. And I do this by looking into air quality data over North America. I have to apologize, I don't know why there is this text line, WIRS AOD assimilation. It has nothing to do with it, it's just a mistake, so try to ignore it. So what do we see here? We see here from 2015 until April this year, in blue the observations, and then the respective values from the global system. We see there are biases. I show you specifically rural station, so we tend to overestimate. But if you look at the development of the biases, they seem to become smaller, which I think is a very good sign that we really made some progress in this area concerning NO2. The picture is unfortunately not so rosy if we look at ozone. Here again, also in blue, the observations, and in red and green, our forecasting system. So in green is the actual system using assimilation, and in red is the system where we don't apply assimilation as a control run. And if you look carefully, you will see that the biases over North America started to increase in later periods, and this becomes even more obvious if you just make a difference plot, and that's of course not very nice, and this has a problem that we have been dealing with for a long time. We think it has to do with emissions. There's no easy solution for it, but it shows that progress is sometimes mixed. Here's yet another example of looking at the whole period as such. SO2, if you look at this picture in general, we would say, okay, things are improving, but there are stepwise changes which have to do with new emissions, which have to do with introducing certain modeling aspects like injection height. So it's a mixed story. What we also learn from these pictures is that the operational forecasts are not a very good data set if you want to look into trends, because we have all these jumps because of the different model versions. So that's why we need to use reanalysis data, and reanalysis data use the same system for the whole period, and they are better suited for this. But when we look at the CAMS reanalysis which we produced, we see sort of also certain differences if we look at the trends. And just to give you an impression of what I mean here, I show here time series over China for the total column of NO2 on the top, and for NO2 the same on the surface. And I also show two different types of plots. So the black curve is the CAMS reanalysis. It's a data set that is based on the assimilation of NO2 retrieval assimilation. And the blue curve is a model run without any changes. So the blue run really represents the emission that we are using. And if we look at the total column, in the blue run, we see over China it increases all the time because the emissions we are using tell us that the NO2 increases. But of course, this was not correct. And it was really one of the successes, in my opinion, of the reanalysis, that when we assimilate total column observations, that then after 2013, the values start to decrease over China, which is far more realistic. And it's really, I think, a very good result. But if we look at the same plot for the surface, unfortunately, we don't see this because the impact of the assimilation of the surface is not strong enough, and these trends are probably not correct. So that's why I think it should be our aspiration for the next CAMS reanalysis data set, which we are starting to produce starting in 2024, that we should be much more careful to get the trends right. So there are different ways of doing this. Of course, we can try to improve the importance of the assimilation by using better and more consistent data sets, by changing the methods, how we do data assimilation, but also that we use emissions that really carefully represent the trends, because that's really essential. So that's really an aspiration that we should have, that we carefully look into the emissions to make sure the trends are correct. Last slide, that's about the new supercomputer. Here you see it here on top, the ETOS machine. And what I show here is a comparison of the performance on the Cray, that's our old supercomputer, and on the new supercomputer, the ETOS. So going from left to right, we see the differences when we just do a model run without having a chemistry and aerosols included. So on the ETOS machine, this runs about in half of the time, and this is the expected increase in computational performance. If we look then at our current system with the CB05 aerosol scheme, we see that things are on the Cray about 3 to 4 times more expensive. And also we noticed that actually the difference or the speed up for the using the chemistry is a bit better. So just looking at this one, the ETOS seems to be more efficient because the overhead, because of the chemistry, is less than on the Cray. Now when we start to use the chemistry for the first time, we saw an increase of the computational cost or the in time by a factor of 3, which is quite a lot just for the stratospheric chemistry. But as a combined effort, we optimized the code a lot so that we can now say what we did with the old system without stratospheric chemistry on the Cray is now as expensive, including the chemistry in the stratosphere on the ETOS machine. Thank you very much for your attention.
Thank you. Is there any question? No? Okay, thank you.